A very warm welcome, everyone. Thank you for joining us today for our webinar titled An Introduction to Machine Learning in Asset Management. I would like to begin by introducing our speaker. Stuart is the Managing Director of Product Strategy at Boosted.ai and has over 16 years of experience working with banking, buy-side, sell-side, and insurance firms on adopting technology to solve business challenges. Prior to joining Boosted, Stu led product management for quantitative finance and risk management at MathWorks, the creators of MATLAB and Simulink. He's interested in the adoption of model-led technology in financial services and enjoys working on processes and technology solutions for computational finance problems. Stuart holds the Financial Risk Manager designation from the Global Association of Risk Professionals and an MBA from the Carnegie Mellon University. Without further delay, I'll pass it on to Stu.
Thank you. Today it's my pleasure to really provide kind of a high-level introduction to machine learning, specifically around the investment management space. So I've got several slides I'm going to walk through to kind of explain a variety of different concepts. Let me go ahead and start sharing my screen so that you can see them. And I'll start the presentation. So kind of the goal for the presentation today is to provide you an overview of the introduction to machine learning from an investment perspective. And then I'm actually going to dive into our product with Boosted Insights and give kind of a high-level overview of what we do in terms of machine learning for investments and how we make machine learning easy and approachable for many different types of investors, but also how we make it explainable so that you can understand what the machine is doing within the context of the investment decisions, the stock rankings that it's creating. So to get started, let me first kind of go through kind of just a definition of what is machine learning so that everybody kind of gets to the same level of terminology that we're using, because the area is very full of a variety of different terminology, and I'll go through a lot of different things throughout this presentation to kind of give you a high-level summary. But really what machine learning is it really started with Arthur Samuel back in 1959. He took the approach of trying to teach a machine how to learn and play checkers is kind of the challenge. The original study he did started with neural networks. The machines at the time were not very complicated and complex to be able to handle more of the capabilities you could do today. And then he actually ended up with what's called a truncated search tree. But really, he kind of coined the term machine learning back in that seminal article about what he did to play checkers against a computer. And the algorithm that he came up with that wasn't a neural network was actually what would be called a search tree today, or a truncated search tree. So in the concept of how he's teaching the machine how to learn checkers, it was learning kind of a search history. So basically it was learning to play 3 plays ahead. So if I was a certain spot in the checkerboard, what would be the move I could make that would maximize my potential payoff 3 plays from now? So it was a very small search tree that they could put in the computer's memory, and it was able to allow the machine to actually learn from several games in over about a span of 8 hours of playing the games. It would then actually have enough knowledge to actually beat him in checkers. So it was really kind of a seminal paper that brought machine learning as application of being able to teach machines to do complex tasks like humans to the forefront of really the AI research at that time. So artificial intelligence has actually been around for a very long time. As a concept, computers were pretty much invented to automate a lot of the processes that people do today. So it's really AI and machine learning and computer science have been integrated for several decades. And this just kind of brings out kind of the whole history of those evolutions. Now, the neural network, the concept that we hear a lot about today, was actually first invented around, earlier in the 1950s. It was really the Perceptron was the first neural network. It didn't find a lot of traction just because of the computational power required to train and develop these networks. And you can see around closer to the 1990s, we start to see more formalization of the neural network as we understand it today, as well as other things like decision trees, support vector machines, logistic regression. Now, if you notice that I said decision trees start here around the late 1980s, but wasn't Arthur Samuel's first thing a decision tree? It is, but it isn't. So the construct that he was using was actually a search tree, which has been in computer science for many decades, and where you kind of just understand the nodes, you enumerate all the possible outcomes. He used a truncated one to do that, so it wasn't really a decision tree as we know them today. Where now a decision tree, you actually calibrate the nodes and let the leaves and branches kind of evolve on their own over time. But really what's driven the availability of machine learning has been the rise of the internet. So with the internet came a lot of data logging, a lot of more data sources. That's been kind of the spurn of all these new statistical statistical learning techniques that came out. So statistical learning was really started around 1990s. A lot of it was applied to a lot of different things you could do with internet data and the big data that we have today, and then kind of grew from there. The deep neural networks that you hear a lot of buzz today didn't really come out until around just close to 2010. And the reason that one came about was because we actually had computational hardware that can now allow us to train these deeper neural networks than we've ever had before. And one of the seminal papers, or the kind of the seminal research point that brought deep learning into purview from everybody today and made it kind of the big, exciting technology that we have today, is that is recognized in the annual image recognition challenges shown over here on the right. So you can see between 2010 and 2011, they're applying a variety of machine learning techniques, but they couldn't recognize objects within an image with a very good accuracy rate. About 30% of the time they were still wrong. Then around 2012 is when deep learning started to come out. So it was a much deeper neural network architecture than they've been using in the past. Coincidentally, with 2012 was the same time GPU training for neural network came out. So now we had computational hardware, the cloud resources, and the big data combined with these advanced machine learning techniques. They really kind of spurned the innovation to drive the image recognition down. And actually in around 2014, that's when the image recognition now beat a human person looking at the same type of images. And we've continued to kind of grow since then. So at that point, when the machine actually beat the human, that's when you see a really big interest in terms of the technology being applied. This is also about the same amount of time when you hear of IBM Blue beating a chess player as well. So all of this technology with the machine learning, statistical learning algorithms came together, and that's what's driving this big evolution of what we're hearing about is AI across all industries. And I'm going to talk a little bit more about the types of machine learning and how they can be applied to financial markets. So the next few slides are going to give you some context in what the terminology is, so that when I speak about machine learning later on, you'll understand what the terminology and what the different goals of these are. But really, there's three types of machine learning: unsupervised learning, supervised learning, and something that's called reinforcement learning. Those are the main three buckets that people put the different types of machine learning algorithms and capabilities into. The first one is unsupervised learning that I'm going to talk about. And really, the goal of that one is I want to give the machine data and have it tell me what it can learn from the data itself. So we're not giving it any information such as an input-output relationship. We're just giving it data and saying, what can you tell me about it? And that's really grouping and interpreting the data based upon the characteristics of the data. One of the first ones that's been around for several decades and might have been used, you might even be aware of, is principal component analysis, right? So that's a method of dimensionality reduction. You take a high dimensional space and you reduce it down to about two factors that kind of explain most of the variability. An example is shown on the graph on the right, where you have a point cloud with a trend. And then you can define that by two parameters, which are basically the vectors that you see that are orthogonal to each other. That's essentially what principal component analysis does, is it breaks down that cloud into two dimensions that explains most of the variation that you can see within the data. A variation on that is actually called clustering. So now you take the data and you look at it in a variety of different metrics. Most of them tend to be a distance metric of some type. And then you cluster and group the data based upon those common characteristics as shown on the plot here on the right. Now, how clustering is often used in finance is you can think of it as a way of detecting outliers. So if you can cluster and group them, you can see when things don't fall into one of the larger buckets you might have. And the other one is you can actually use it to detect changes in patterns, changes in behavior. One example would be is if you looked at game prior to the retail investors driving up the price to put on the short squeeze. They had a certain characteristic behavior before that, then afterwards the behavior changed. So clustering is one algorithm that you can use to detect changes in behavior or changes in the way of patterns of the data. So now if we move over to supervised learning and then even reinforcement learning, supervised and reinforcement learning share very much the same outcome, that they both want to develop a predictive model based upon some input and output data. The difference between supervised learning and reinforcement learning, we'll get to in a minute. But really what you do is you give a supervised learning algorithm input data sets, output results, and then have it try and learn to match the input to the output over a training set. And as it does that, it learns patterns within the data that map the inputs to the output space. And that's how you develop a prediction algorithm. One type of prediction is classification, where you might have different types of categories. So a very common one is, recognizing different kinds of objects, a cat and a dog, with some kind of probability related to that. So this is one of the big areas of classification that you'll see is like image recognition. More specifically, in the finance space, classification is often used for many things like fraud detection. So now you can look at a bunch of input and output data and detect when behaviors change and classify them as good behavior, bad behavior. You can also classify stock market movements as going up, going down, or going sideways. So those are the types of applications for classification. The other one that's very common that many of you probably have done and didn't know it is that you've been a machine learning engineer in the concept of creating a regression. Anytime you fit a curve, that falls into regression, that falls into the supervised learning category. A good example is a typical market line you'd see here where you have alpha is the excess return to some market or some index, and beta is the slope of that curve. Now, the difference between what you might have here is you can see that the equation has a defined form. We're fitting a model to it. In more modern machine learning, we let the machine kind of define what the model form would be and even add many, many more parameters. So if you think about this curve and how you might use it in investing, you might add different factors such as momentum, such as volatility to this equation, and use that as a predictive variable in here. So the machines that we give, we don't necessarily define the form of the regression equation anymore. We let them do it. And many of the black boxes actually have a complex technique for doing that. But this just kind of illustrates that many of the statistical techniques you've probably used in the past at some point really kind of fall into the area of machine learning. The main difference is the scale and complexity between what you might be doing and what we're allowing these algorithms to do themselves. And then the last category is reinforcement learning, and how it's different than supervised learning is that you don't necessarily give it a ton of learning data. So in supervised learning, you need to have a very large training set so that it can learn all the variety of different patterns and all the different kind of use cases or edge cases. In reinforcement learning, you give it inputs and outputs in terms of playing a game or a simulator. So you can start with very sparse data sets. All you need to do is provide it kind of the rules of the game, if you will. So it needs to learn from the rules of the game that's been provided or the policy, how to play the game and get outcomes and rewards. So in that way, a lot of the reinforcement learning doesn't require a vast set of data, but you do have to have a good simulator or a good way for the machine to learn, either interactive in a real environment or through a simulated environment, so it can make mistakes and learn over time. And that's the difference between supervised and reinforcement learning. Is that supervised learning is you're telling it the relationship and kind of saying, figure out how to match those. Reinforcement, you're giving it kind of the rules and say, we want you to maximize your benefit, but the input-output relationship is more fuzzy and not as well defined in that particular case. And reinforcement learning probably has more longer-term potential for finance as it can learn the complex behavior of the markets as they adapt. So one of the challenges with finance markets is they tend to be non-stationary. They're modeling real human behavior, so they tend to change over time. If you think of the stock market, it's always changing. Look at what happened during COVID. The experience we saw there was something that was never seen before in the history of the stock market. So those types of things is what makes it really hard to use machine learning in finance, is because the complex behavior is always changing and modifying, and it's not something you might have seen in the past data set. That's where reinforcement learning actually has a lot of benefit in that it can adapt and kind of learn from that in a shorter time frame and not require as much data. So that kind of gives you an overview of kind of the different applications. This just gives you a list of kind of all the different algorithms that can be employed in those different areas. Some of them you may have heard. I mentioned principal component analysis, linear factor analysis. If you're in statistics, you probably heard about before, linear, nonlinear regression. And there's a variety of different ways, and these are just the main techniques. But the one that you can see that kind of spans most of the area is decision trees, as well as deep neural networks. Those two are actually widely usable across almost all of these different applications. And in particular, that's why you hear a lot about deep neural networks being applied in all these spaces, because it can be used for dimensionality reduction as well as prediction. And I'll kind of dive in a little bit deeper on why this particular framework is very flexible. But there's kind of a blurred line between deep neural networks and deep decision trees. Those can often be applied in a variety of different places as well. So I'm going to kind of give you some more examples and dive into a little bit more between what's traditional machine learning and this new area of deep learning in particular in a few slides. But I want to kind of reinforce that one of the values of the machine learning approaches is that, we're not enforcing a model that it has to learn, we're letting it learn the model. And I think a good example is the one shown here from a McKinsey analysis, basically on mortgage lending. So over on the left, you have an actual phenomena. So the person here is, 25 years old, highly educated with a master's degree. They're a fashion industry employee, so you might think that might not have high earnings income potential. but they're coming from a rich family. So you know that this person is a very stable person to lend to. And if you look at the kind of the heat map that's shown, you can see there's this pocket in here that tends to be a region where there's good opportunities to lend to good creditworthy people, even though the area around it might be red. Right. The traditional approach is we typically take a model and try and apply it to our data and fit it as best as we can. The section in the middle is the traditional logistic regression approach, where you define a nice smooth curve. It's a nonlinear model, but you can see it has a smooth behavior that tries to fit all the data, and you can see how the curve approximates different kind of lending grades as it marches through the data set. What you can see is that it still misses this one. So even though we're capturing the major dynamics that the data is telling us, we do miss some of these highly nonlinear areas that can cause problems for traditional models. The benefit of machine learning is that it actually is, since it's a highly nonlinear modeling capability, it can actually map out those domains much better. And you can see the way the model learns here is you can see that there's actually this island within the kind of the red zone that's a good stable island for, providing credit for a good lender. Similarly, you can see there's these other islands out in the good areas, that provide, worse lending and kind of what would probably be considered a good lending scenario. So the nonlinear nature of this allows us to capture effects in the data that we can't really capture with traditional techniques. And that's why machine learning is highly valuable. But one of the challenges here is if you didn't see this map as I present it to you, the challenge would be to explaining how the model's coming up with this, because it's not simple and easy to describe the nature of the surface on the right. The one in the middle we can explain, it's highly transparent, but we do tend to have a few areas where we lend to people we probably shouldn't be. So that's kind of the challenge we have. And there's a lot of research going on now to really make machine learning capabilities more explainable, so that you can dive in and truly understand it a little better. So to give you a feel for the difference between what is traditional machine learning and what is called deep learning, I'll first present kind of the traditional machine learning approach. So let's say you had images of cars, an Audi Q7 in this case. You run a variety of different images through kind of basically a feature extraction process. And one of the main ways of doing that for image processing was to do edge detection. So we detect all the edges in the image. And then from the edges, we run that edges through a model that says, based upon the way you're put together and the way that the edges are assembled, you look more like an Audi than you do, say, a BMW 640. And that's how the traditional approach is done. There's often a lot of feature engineering to get it into a state that we can then put into more of a transparent model, even if they might be a traditional machine learning. Is typically you actually have a good feature set you put in that actually has a lot of description about the system already there. But one of the things you notice is I go from the image over on the left, which is full color. You can tell that the car is silver. You can see that there's trees and there's a road in the background. A lot more detail about the car, the grille, the Audi symbol on the front. All of those things tend to lose information anytime you do a feature transformation. So that's one of the challenges, is that anytime you do a transformation, you lose information content. So if we can keep that information content, as well as give the machine what it needs and let it learn from all of the information, you can often get a better predictive model. And that's really what came out of the deep learning, is that they took away the feature engineering and put that in combination with the actual model development process. So in a deep learning architecture that would be learning from this one, what it actually does is it learns both a model and the features at the same time. So that's one of the challenges with explaining these models, is that they learn both feature and model kind of intersected together. And it's sometimes hard to tease that out to explain why the model makes a certain choice. But that's really what's going on under the hood, is it's learning a lot more from the data that you give, because it's got the full information content and it's allowed to learn everything it can from that data set. And this just gives you kind of a view of how the different layers might first start out with first learning to just detect the different directions of angles within the image, getting a little bit more information about structures like maybe a tire, maybe a headlamp. And then you get to the final one, which actually has more of the actual car shape in a variety of different ways. And that's how deep learning is different, is that you're actually allowing it to kind of learn what we used to do kind of manually in a traditional machine learning process. Now, the other thing that's really different about deep learning is kind of the size of the model, or the depth of the network in this particular case that we can create. And to give you just a feel for how neural networks work, they're basically just a connection of a variety of different inputs with some kind of weighting. So that's a parameter, a scaling, multiplication factor of some type. And then you have an input function, and that's how it aggregates all that data together to create an output. In this case, it just happens to be a summation aggregation point. And then there's an output that often has an activation function on it that puts a weight. How important is this particular thing that we're getting out of this first stage of the network in terms of the overall output or prediction? Now you put these together in a much deeper layer, and this is what's typically viewed as a shallow neural network, where you have the input layer, a couple hidden layers, and then the output layers that give you that. One thing to notice though is that you can also create two different outputs, so it can be learning. Maybe one could be the type of color that's coming from the image. The other one could be whether it's a car or a dog, as an example. So you can actually use the neural network and train for more than one output at the same time. Now, to break that back into how that worked in the kind of the image processing example I showed before, here's an explanation for taking a picture of a dog. You break that down into individual pixels that are then run through the first layer, where it's detecting what that's really the inputs to the model is what color is the pixel. Then it goes through a kind of a layer that detects the edges, then the combination of edges, and then features. And so this is how it's learning from the actual data that what features are important in terms of making a prediction that this is a dog versus something else. Now, this is still represented as a very shallow network. In reality, these things can be actually very deep. So you can have many, many different layers that are doing a variety of different types of things to the data as it flows through the network. And this just kind of gives you an example of what's involved in terms of taking a seaside input and identifying the different objects that are within the input, like the boat, the water, land, things like that. Now, one of the things with deep neural networks is that there's often a lot of art kind of to how many layers you put together and put this together. So a variety of different neural network architectures have been put together to address different types of problems. And this just kind of gives you an overview of all the different types of standard network architectures that are out there today. So there are a lot of different ways to address different problems. And these are different network architectures that have been found to address certain problems specifically. So this just kind of gives you a feel that, neural networks being applied to solve problems is often a little bit of art and a little bit of science to do that. Now, I want to actually start diving into more like what we do here at Boosted Insights and give you more of a feel for the types of algorithms that we actually use to help guide a variety of different investment decisions. So I'm going to go through kind of the traditional approach, more kind of like a decision tree approach, and then one of the algorithms that we do. And then I'll actually dive into a brief demo to give you a feel for how Boosted Insights works. But basically, the chart over here on the right kind of gives you almost a heat map, but it gives you a picture of good performing investments, poor performing investments, ones that are somewhere in the middle, against two different factors, right? So we have price to earnings ratio on the x-axis, and then we have earnings growth on the y-axis. Now, a traditional type of approach might be, if you think of a fundamental analyst, they typically say, I want to screen stocks that have a price to earnings above 20, as an example, or between 0 and 20, and then you might have an earnings growth of 10% or greater. That's kind of highlighted in the box there in the top. And what you can see from with the box is that it does have a decent number of greens, some reds, and some neutrals. So really, when you're defining a rules-based approach like that, the whole objective is to try and find an area where you have more winners than losers. And that's kind of the traditional approach. Now you can see that it doesn't capture all the information content that's in the slide, but it does give you a feel for how different decisions can be used to select an investable universe that meets your particular goals. Now, the other one is to actually use more of a traditional statistics approach as well. Let's try fitting a curve to it, right? And this one shows if you fit a curve to it, what would that look like in terms of the linear for good performers, a linear model for neutral, and a linear model for bad performers. So in this way, it breaks the universe kind of into different regions. Neutral is pretty much, you can see that they span the whole spectrum of the map that we've seen there. The one that's the linear neutral is the orange line that kind of goes up and to the right a little bit. So as you go further out in the price to earnings and up a little bit more in feature growth, that tends to be where kind of the direction of the neutrality goes. And then the good performers are the blue line, which is pretty much flat. So if you look at using linear regression in this case, it's kind of really hard to use it because it's not differentiating on price to earnings in any way. So it kind of says everything on the space looks good. And very similar for the bad performers, is it slightly sloped down. So what it's saying is kind of the same thing, is that it doesn't really differentiate a whole lot on price to earnings ratio or price to earnings growth. So linear regression in this case isn't really a good model because it's not giving you good information content in terms of where to invest, compared to the prior approach, which is more the traditional approach. Now, the other approach is to actually kind of build a decision tree on this. And this just gives a high level example of what's called a decision tree. What we have in Boost Insights is something called the random forest, and I'll explain that in the next slide, between a typical decision tree. But what we have is a decision tree here that basically has different decisions based upon the value at the node. So you start with the earnings growth. Anything greater than 0, it's got 2 decisions, right? One could be 10% growth, or the other one would be less than 10% growth. So that's kind of a branching decision. Then it goes down and has a decision for the price to earnings growth. And then you can get a sell and buy signal. And graphically, that's represented as kind of the 1, 2, and 3 boxes in the chart here. So now you can see how it's choosing a little bit more of a complicated investment space compared to the traditional method, but it's picking up a lot more potential good investors than maybe potential bad investments in this way. Now what we do with machine learning is we don't build small trees like this. This would still be a tree that maybe a person would do. So this is almost like our traditional approach, that somebody could still do this in their spreadsheet and build a screening technique like this. What we do with actual machine learning is build much more deeper trees. And also we build many varieties of them. So the random forest is actually not just building one decision tree and fitting that to your data, but building many decision trees that have a variety of different conditions at the nodes. So in this example, what we have here is we have 3 or more different decision trees that have different paths to them. And what we're really doing is we're changing the structure of the tree, but also we're looking at changing the values that these things make decisions upon, and let the machine kind of perturbate on those. And the idea behind this is, if you have decision trees by themselves, can often be what's called a weak learner. So they might have not really strong predictive strength, but when you take a bunch of these weak learners that are different all combined together, they become what's called a strong learner. It's kind of related to the wisdom of crowds. Like if we poll a crowd, we get much more ability to predict the future than if we poll an individual person. So it's based upon that concept, but it's really called the random forest because we're building a bunch of random trees, and then we're voting on the outputs to create a decision based upon that for the final class. And that's really the goal behind decision forest, is that it creates many different models, many different trees of different types, and then it takes the aggregate from that and says this is what most of these models are saying. And that's how these models are typically used in terms of the random forests. Now, one of the things that we do that's proprietary within Boosted Insights that's a little bit different is we look at the problem more like the way an analyst would look at the problem. So what we do is we actually have an algorithm called the Battle Royale with noise reduction. So the Battle Royale part, what that's doing is it's taking, like similar to what an analyst would do, is taking the different stocks within the universe and comparing them head to head and seeing which one would win on a variety of different parameters. The part that's noise reduction is what that does is it injects some randomness to that process so that you can avoid kind of some local optimal and try and get a better solution. It's also better when you have highly noisy types of data sets. So it comes to a solution much quicker in that particular case. So that's kind of the difference in kinds of the different algorithms that might be applied in terms of an investment space. But what I'm going to do now is actually kind of dive into the Boosted Insights, do a quick demo just to give you a feel for what it can do, and then we'll come back for some questions. But before I do that, I want to really kind of set the stage on what is Boosted Insights and how does that work. So the way it works is I like to think of it as it's AI, but it's really kind of an augmented intelligence, not artificial. It's augmented. So what we do is we use the machine and some of our proprietary algorithms and big data, but we also use your expertise. So you put in what kind of portfolios you want to build, what kind of stock universes you want to invest in, the variables you feel are important, any additional data sets that you might find, like alternative data. So you bring in your expertise of the domain you do, you combine that with our data sets, our machine learning algorithms that can learn from the data, run that through Boosted's machine learning and portfolio analysis routine, and then you get a bunch of different portfolio ideas that you can do. So that's really the way I think of it, as an augmented intelligence platform, because it still relies upon you to decide what's the universe, what's my investment goal, what is it I'd like to build, and then let's build it together with machine learning and access to large data sets. So in a second, I'm going to dive into Boosted Insights and kind of show you a demo. But the way that it really starts out within Boosted Insights is first we start with building a model with your selected universe. So you need to identify what is this type of investments you want to invest in. Maybe it's the S&P 500, maybe it's a global investment ETF. That's your choice. That defines the universe. You'll come up with other input factors. So if you think analyst expectations are important, for example, maybe market cap is one of the things you think is important. You get to select a variety of different variables that you can then also put in there from the fundamentals, as well as a lot of technical indicators. That universe, your objectives and the input variables go into the machine, and what the machine does is, depending upon the algorithm you choose, it then runs through the data, does a back test over history, and gives you a result. And that's kind of what's shown in the slides on the bottom. But another output of it is we don't just give you the investments or the portfolio, but we give you a stock ranking. So you can use the thing to rank every stock that's in the universe you have. And then the machine tells you why it likes this particular stock over another one. So you get a ranking of the entire universe from top to bottom. And then after that, once you built your first model, you can go in and then start tweaking it. So you can add a variety of other constraints that might be important. You can look at the results that you got from the first test, see which factors tended to be important, maybe add more weights to them, remove the ones that are not important, and rebuild new portfolios and create new ones that give you good ideas. So with that, I'm going to go into Boosted Insights. And what I'm going to try and do within a few minutes is just kind of give you a feel for what the platform is and what it can do. And kind of the different kinds of ways that we have of explaining what the machine is giving you from the outputs. So I'm just going to start. So when you first come into Boosted Insights after you log in, you get a screen like this that actually shows a variety of models that you have or that might be shared with you from the other people's on your team. I'm going to go through an example of how you build a model. I'm not going to complete it because it takes time to run the backtest and do it, and you won't do that in the time frame of this webinar. But I'll show you a real quick example of how you build a model, and then I'll flip over to one of these models that have been built before and kind of walk through that. But the first thing you do is if you want to build a new model, you come in, you give it a name. I'll just call this Stu's webinar. So we give the model a name. The next thing is you can see there's over on the left, there's kind of a checklist for you to go through as you build your model and when you select things, the different things you can do. But the first thing you do is you select that model choice, right? So these are the selections that we have for here. There's a couple that are proprietary, and then there's a couple that are open source algorithms that you can try. Quite often we recommend starting with the Battle Royale or Battle Royale noise reduction because they tend to do the best that we found from our testing. I think there was a webinar about a month or two ago that kind of talked about some of these and the performance some of them had, that if you're interested in them. But as you click on these, they do give you a little bit description of the type of algorithm, kind of the benefits of both in terms of the cost, performance, accuracy. So you can get a feel for the variety of different things. The Battle Royale does tend to be more expensive in many cases, but it's one that we do recommend. So I'll start with that one. Oh, and then after that, what you want to do is if you have any custom data sets, you can upload them here. This is where you add any other data you have, any other stock information that may not be in our database, any alternative data, things like that. So it's the nice thing about our platform is that we have a very rich universe of equity data, but if you want to bring other data sets to that, you can as well. In the goal selection, now here you just want to kind of select something that gives you a feel for how your optimization is going to produce a portfolio. You can maximize alpha, raw returns. You can choose your benchmark. You can also define a custom equal weight or market cap benchmark based upon the universe you select. So in this case, we're going to just select the SPDR ETF as our universe definition for our benchmark. Later on, I'll choose that as my stock universe selection as well. So we're gonna trade out of the S&P 500. This is where you actually choose your stocks. So you can create your own from a template if you have a custom one. You can also select them by the different regions, different ETFs, if you will. You can build your own templates. Some of them are provided in the demo account here, and any shared templates that you have. So if you have teammates that have been building custom universes, they can share them with you. They'd show up here. In this case, I'm just going to go through and I'm going to go to the index. I'm going to choose the North America. You can build from a variety of one, but we're just going to use the S&P 500. So we'll do the SPY membership. So we're going to grab an ETF that'll serve as our benchmark. All of those components will be the universe, and we'll be allowed to trade anything in here. And as you can see, when you select the universe, you can see that as of the current date, there's about 499 stocks in this universe. And as you move the slide around, you can see how this would update and change based upon what was in the current ETF at the time. Now, that's one of the things is this universe defines what's available for your algorithm to invest in over time. So as things come in and out of the universe, maybe stocks or new companies are added, maybe companies are dropped from the S&P 500, those would show up in your universe over time as well. So this automatically takes care of all of that for you. The next thing is you can then go through and define the backtesting range and the training frequency. So the backtesting gives you the range of backtesting you're going to do to build your first model. We recommend that you at least have about 10 years of data typically to start. And then the other thing is the training frequency. So this is how often the machine learning algorithm is going to retrain based upon the past history it's seen. I'm just going to use the defaults, but other options here for you would be like semi-annually or even quarterly. You can change how long this does. The more data you have, the longer it takes to return a backtested result. Now, this is a section where you can actually create a variety of variables that you might want to do. So one of the things you can do is you can add variables. As you can see here, you can even define certain parameters of them. You can define your own. This allows you to name variables, see the coverage that's available, and things like that. So let's just go ahead and let me just select a couple to move forward. And then the portfolio settings. So this is where you define your initial portfolio optimization problem, how much you want to go long and short, the number of stocks you want to have. And then there's a variety of other factors here that we can get into detail, but I would just use the defaults to start. And once you do that, excuse me, it'll go off and it'll create a backtest and then you'll get a result. And to give you a feel for what that looks like, let me go to the S&P 500 quarterly, which is a model that was created earlier. I'm just going to walk through this to kind of give you a feel for what it looks like, and then some of the explainability capabilities we have in terms of explaining how the machine is predicting things. But now each one of these tabs here are different portfolios that are using the same model. So these have different settings depending upon what was the objective of the portfolio. But you can think of it as you have your model, and then I can build a bunch of different portfolios based upon that model. So in this case, we use an S&P 500 universe. A battle royale noise reduction was the model. The objective is to maximize alpha in this case. 60-day investment horizon, USD, North America region. How it rebalances is the first trading day quarterly, and then it's going to retrain quarterly. So this is a quarterly one. If I look over here, there would be a monthly one that would train monthly or rebalance monthly. It's going to, so you can often also set like what is it's going to use for its trading entry price, whether it be open, VWAP, or close as examples, and then what the benchmark is. And then over on the left is a variety of different information that you can get about the traded portfolio results and drill into the details with as much desire as you like. But the first one is the portfolio summary tab. Just gives you a variety of the summary of the different portfolios you might have built off this model. The other thing is you can then go to a tear sheet. So if we take the market cap as the one that's active, this is the current tear sheet for this particular performance. You can see there's a graph here given the historical benchmark performance. The option we give you is you can do a back test, and once you're happy with a model, you can take it live, and then it will actually update daily with the market conditions and show you how it would be performing live. So we took this model live around January 1st of 2021. You can see the live performance. The black line is the actual benchmark, so that would be the SPY. The blue is our actual returns. Things you can dive into would be total returns, turnovers. You can then dive in and look at the factors themselves, any particular one you want, like volatility, momentum, a variety of things. Now, one of the things that we offer that's different and unique, and this comes out of our proprietary algorithms, is these machine learning factors. And these machine learning factors, you can think of them as they're kind of a measurement of risk and return. And I'll kind of dive into that in a little bit later, but each one of these you can think of as almost like a principal component, because machine learning factor 1 is orthogonal to machine learning factor 2, and so on and so forth. Typically, the first couple machine learning factors that we provide you have the most information relevant to really making trading decisions, and then the information decays as you go further down. But I'll talk a little bit more about the machine learning factors later on. And then you can also look at a variety of other things as well. I'm not going to go through this in complete detail, but there's a variety of different ways of looking at the information contained within your portfolio and the results. The other thing you can look at is really, you can look at accuracy. So you can see your performance, the hit rate, the excess return by 5 days all the way to 2 years. So you can get a feel for how different things are doing. Now the quantiles that are shown here, this breaks it into 5 quantiles that correspond to some of our rankings. You can then also change these to deciles or ventiles if you prefer to see more details as well. Now, diving a little bit into explainability. So we have a machine that gives you these signals that you can use to help optimize your portfolio or choose different portfolios. So what are the explainability capabilities we have? So one of the first ones is just kind of giving you a high level view of the features importance through as like a word cloud. So here's a word cloud that says all the features that were put in this model. The bigger the size, the more important it is. The smaller, the less important it is to the particular model. You can see this one tends to like price momentum, the CAPM beta, some analyst expectations. There's also a tabular view that you can look at. So this gives you the same information in a tabular view and the percent importance to the model. Now to keep in mind that these are all the factors kind of aggregated together into that category. So if we had many different price momentums, like if you had a 6-month versus a 12-month price momentum, those are aggregated all into one particular factor here. If you want to dig into more details on some of the nuances of the different factors, you can go into the feature importance, which then will give you kind of more detail about the specific feature you have. So this breaks them all down. It gives you the impact on the model output. So this is a Shapley plot, if you're familiar with Shapley plots and how those work in explainability. But it's basically a local interpretation of how well this factor's influencing the decision of a stock being a good ranking or a bad ranking. And then there's a signal for the stronger sell side or the stronger buy side. Its feature importance overall. So that gives you a feel for looking at the features and how they're important. Now, I mentioned about the stock rankings, and one of the things that we do give you as an output is the rankings. So before I get to there, I'll just explain some of the other ones. So we have some of the typical other things you would look at from a portfolio, such as what is the drawdown, the actual holdings you have, the allocation by different sectors, what variables are important, and then the actual trades themselves. So that gives you a detailed view of kind of all the trading activity for your portfolio. But one of the most useful things is the rankings page, which actually gives you that information, but it ranks the whole universe by stock and tells you which one it says is the #1 pick versus which one is the #2 and so on. And here's an example of that. So in this particular case, at this point in time, it's saying that Facebook is actually a good buy. It's got the highest rating of 5. One of the key factors explaining to that would be the log market cap. One of the key drivers of maybe not being there would be the market ratio. And you can actually drill into these into more detail. And one of the things you can do is you can see more of the factors that are important as well. And one of the things you can do is actually drill into a 1-page stock summary, which gives you even more information on why Facebook in this particular instance is being declared a good one. And what you can see is the actual rating of how the machine ranked Facebook over time. Facebook's price history, kind of the recommendations, as I showed before, and the excess hit returns, as well as the score deltas. So this gives you some information into why it's saying Facebook is a good one. These are the factors that say make it a good. These are the ones that make it maybe not as good. And then both these factors added together kind of give you that score that you saw on the previous page. Let me move this out. So if you see the final score, that's kind of what comes up to add up to this is all the different factors summed together will give you a final score. So that gives you a feel for how you can use it to do security screening, dynamic stock picking. These do change over time. I did mention a little bit about the machine learning factors, so I'm going to talk about that real quick, and then I'll break so that we can discuss any questions that have come in. But there are a variety of other diagnostic tools here as well. But I mentioned the machine learning factors and these semantic risk groups. So one of the things is if you look here, it tells you the machine learning factors and kind of what's really driving that machine learning factor and why it's saying certain stocks might be better than others based upon this factor. You can see in this example that it says that, there's cruise lines, airlines, oil and gas. This is risk group B versus something like called risk group B, software and medical. So one of these is really helping drive that machine factor and explain that mostly the cruises, the airlines, and oil and gas are all kind of moving and behaving together. So there's some kind of characteristic that's making that fall into the risk group A. Software and medical are behaving similarly in another way, so that's why they fall into to risk group B. And this factor alone explains 47% of the variability you see within kind of the model prediction to date. Now you can go down and see that as the machine learning factors, you get decreasing returns. So it's usually the first three that are important and useful to help you building model decisions. Machine learning too, you can see that it's grouping website and technologies together, as well as insurance, natural gas, and foods is the other one. So this is just kind of gives you a high level overview of how Boosted Insights allows you to build portfolios, look at all the results, look at all the signals that you can use for optimization, portfolio analytics, and then the custom machine learning factors. So with that, I think I'm going to make sure we have time for questions. So I'm going to break here and go back to our moderator and take some questions.
Thank you for a great presentation, Stu. There's a bunch of questions that we have. Let's try to take most of them with the time we have at hand. First one, can you explain how signal generation works along with back-tested results?
Sure. So the way that the platform works is we take your inputs, we run that through the machine learning. So we basically take all your variables in, we do some feature normalization on them, and then we send them through a machine learning algorithm. And what the machine learning algorithm does is it then generates all those signals that are used as an example for the stock ranking. So you get your fundamental factors out of there, you get our machine learning 1 through 10 factors out of there. And then all of those factors are then put into your portfolio analysis algorithm, which will then do the actual trading. But what it does is it does all the actual trading in history based upon the constraints you define. Like when you buy, is it in the open? Is it the closed? How often do you want to retrain your model? How often do you want to train? So all those portfolio parameters can be put in there. The other thing is that, you know, all of those signals, you can then decide how much to weight those signals in terms of making investment decisions. So if you liked volatility, you can weight it higher, so it'll trade more on a volatility factor. If you like it less, you can dial it down. Same thing for others. So you can actually put constraints on all of those different factors that are basically signals that are put into the model. You can then constrain them in the ways that you see fit. So if you like the machine learning factors, you can use them. You can remove them and not use them. You can just use something like analyst earnings announcements if you like that. So it allows you to completely customize your portfolio objective the way you want. The portfolio optimization is very capable in a variety of different ways. You can set a variety of different optimization targets than what I've shown. We did optimize alpha. You can do that by quantile. You can do raw. You can do Sharpe ratio. You can do a variety of other optimization techniques as well. But basically, there's kind of those main steps. You select your universe. You let the machine learn from it. You take the signals from the machine and run that through your portfolio analysis routine, and then that gives you kind of your investment decision. So the portfolio analysis will actually make the trades based upon how you define your trading universe, how many stocks it can hold in any particular area or sector, and the overall objective. Now, the portfolio analysis does its best to satisfy all its constraints, but if some constraints can't be satisfied, it will drop some of those constraints. So it's not a portfolio optimization routine that will fail if it's over constrained. It's going to drop the ones that are not as constrained and continue on. So you'll always get some kind of traded portfolio out of this.
Thank you. Next question. I'm interested to see how AI can be used in both screening for trade ideas, monitoring news flow on existing positions, as well as possibly using AI to identify patterns for trading strategies.
Right. I mean, that's a pretty complicated question. So I think there's trading strategies, there's using news. What was the first part?
Screening for trade ideas, monitoring news flow on existing positions.
Right. So one of the ways you can use it, I mean, I'll talk about how Boosted does it, and maybe some other ways you can do it too. But within the Boosted Insights platform, you can use the stock rankings to screen for different trading ideas, right? So you get a list of the best and worst ranked stocks. You can decide how you might want to trade them. So you can think of it as your own personal stock analyst. They're giving you recommendations. You can decide how you want to include them in your portfolio or not. So that's one way that Boosted can be used. The other one was the news analytics. So our platform itself doesn't have any news analytics within it. If you wanted to use that, that would be something you'd have to add separately. But there are a lot of other ways that you can look at taking news, doing natural language processing for like sentiment analysis as an example, and then using the sentiment to generate signal for trading. So within our platform, you'd have to provide the sentiment signal. So you could get sentiment analysis from a variety of other news vendors, but that would give you a sentiment signal that could be put in the platform and used as part of one of the other ones. The way it would work is if you had a sentiment analysis input it to our platform, it would still go through the machine learning algorithm, and then those machine learning factors might be able to use that to enhance the way it's predicting which stocks would be the best and generate the ranking results. I think that answered the question. Let me know if I didn't answer it completely.
Identify patterns for trading strategies. If you didn't, if you want to elaborate on that.
Oh, identifying patterns. So I mean, that's what machine learning does. It basically looks at the past, identifies pattern, and projects that into the future. So within our platform, those machine learning factors that I told you were there. Those kind of help identify different patterns of when to buy different stocks and why. The rationale why is it's got a very deep decision process underneath that, so it's not very easy to explain why the machine learning says this particular pattern is there. We're working on techniques to bring that forward in the interface so that we can expose why these patterns work. So maybe in a month or 2 months, if you come back, we'll be able to talk about patterns and how they were recognized in the platform for decisions. But I mean, in general, that's what machine learning is good at detecting patterns. The trick comes about explaining the pattern and why you should trade on it, because sometimes it won't make sense. Sometimes you don't have enough information about it. So, you know, the machine learning factors, that's why we did the semantic scoring, was to give you a better feel for what was driving the machine learning factors. It's not the only thing that's driving it, but it gives you a feel for it. In large part, it was being driven by the cruise line sector, as an example. So that's really how you can use it. But machine learning in general can help you identify a variety of different patterns. It depends on how you train the algorithm to identify them. I'd say one of the challenges, though, is that because you have to use a dynamic pattern identification process, because the markets are always changing, human behavior is always changing. So what you identified 10 years ago likely won't persist very long into the future. So patterns are always adapting and changing. So that would be kind of the big thing, is make sure you're developing a pattern recognition process that can update with the current situations in the market going forward.
Thank you, Stuart. How can I use boosted insights to construct a Forex trading portfolio?
Forex trading, so our platform currently doesn't have Forex information in it. You would have to add that yourself through the custom input. You could add a bunch of bonds and kind of approximate what would happen, like bonds from a variety of different industries, and trade those. So that would give you some Forex type trading capability within the platform as well. But we're not necessarily geared towards Forex trading. We're geared more towards stock picking and ranking. So if you could do that with bonds, so that'd be a way to approximate it. Foreign exchange directly itself would be hard to do within boosted insights directly.
Thank you.
But you could use like the bonds from different countries as a way to rank them and maybe understand which countries might be better to invest in and maybe why you might be trading different foreign exchange. So you could use it for idea generation. It would take a little bit of mapping from what we do to the actual foreign exchange market you might be participating in.
Thank you. Very quickly, how is AI used in stock screening, factor risk exposures, and portfolio optimization? If you'd like to answer that.
Well, I think that was pretty much answered throughout the presentation, but just to reiterate, so what AI did is it took your universe of variables, all your investable assets. The Battle Royale actually took every stock and broke it into a ranking. So it said, here's best stock at any given point in time to the worst stock. So that's really how it was working. It also gave you all those signals. So you still got your momentum, volatility, any other technical indicator you want as a signal out that you can look at and see how much it contributed to the stock ranking as an example, or you can use the machine learning. So that gives you kind of the signal generation. All of that can then be put into the portfolio optimization or analysis routines, which will then take that information and construct a portfolio of your definition and then show you how it would have performed in history. And then you can also turn it on live and see how it performs going forward. One mention, I think, for the back testing is, so we don't have any look ahead bias in the back testing. What it does is it goes back 2 years beyond where you say you started. So it trains on 2 years before, and then it starts to move forward. So it's really more of a walk forward testing than really back testing. But it does need about 2 years of data to get started to kind of seed the initial parameters for the machine learning algorithm to learn from.
Thank you. How will the asset management industry evolve going forward, and how can I best prepare myself as an equity analyst?
Well, I mean, that's an open-ended question, but I think the reality is that machine learning, artificial intelligence, it's here to stay. So more and more investment decisions are going to be in some way, shape, or form supported by machine learning. So I think there's kind of one mentality that everybody thinks, well, AI is just going to be able to do it all for me. So it's kind of artificial intelligence. I think we're a long way from really truly artificial intelligence in terms of financial market. I think it's more like what I said before, is that it's augmented intelligence, right? You take your expertise, your domain knowledge, your understanding of the market, and also your understanding of what it is you're trying to invest in and the goals, and combine that with a machine that's then going to help you optimize that. So I think as an analyst, something like the Boosted Insights platform is actually very good for that, because we can help you understand the stock universe ranking based upon what the machine thinks, and then you can use that to dive deeper, recommend other things as well, or understand more details why a certain stock is that way. So, rather than having to do all the analysis yourself, you're getting kind of this big data perspective. You don't have to do that. You can spend more time on kind of the more nuanced things that might add value beyond what the machine can learn from. So that's where I think, kind of the combination of a machine, your industry or domain expertise can then be used to provide something really beneficial to your clients.
Thank you. How do you avoid overfitting?
Overfitting is always a challenge. It's a good question. So what we do within our environment is we do the best we can to look at the outputs of the model and make sure we're not overfitting as much as we can. So we try to choose the most parsimonious model, but we still leave a lot of the flexibility to the end user. So in the platform, I showed you all the variables that came out to be important, right? So what we do is that in importance, there's probably a lot of variables in there that really aren't adding much value to the overall decision the machine's making. So in some cases, the machine's giving you a little bit of an overfit there, but it is trying to tell you which ones are not important. As you remove some of those, that will then change the results and make things a little better. So we give you the tools to make the best portfolio you can. We try to make our machine learning as I guess you could say adverse to overfitting as possible, but it's not always possible based upon the whole entire universe. But we give you the tools to understand why it's making a decision. You can add and remove different things from your stock universe to then help it make better decisions. So a lot of it is you'll see how the portfolio behaves over time, and then you can adapt and adjust to that.
Thank you. Do you use point-in-time data for your data sets?
Right. So we use daily data. So what we have within our environment is we have daily data for a variety of different global exchanges throughout the world. You saw a preview of that in there, but what we have is all of that data is delivered to us daily. So everything is, you can go down to a daily level of granularity if you want. If you want to go beyond daily, we're not delivering things in real time. And there's actually in our platform, there's about a 2-day delay from getting all of the dividends and some of the other features. Or factors and fundamentals. So our platform is about 2 days behind in complete information for what we provide. So you can trust it for about 2 days back. We do get daily price data, and that's updated quite frequently in the platform. So that's up to date every day. But in general, our processes, we ingest all the data, we run all of your models in the morning, and then it's delivered in that next morning. And some of them will have incomplete information for 2 days related to things like dividends, any adjustments that might have done to stock splits, things like that, or if we just haven't gotten the fundamental delivered from our data providers at that time. So it's down to a daily level kind of granularity.
Thank you. How stable is this? I understand there's randomness in the way machines learn. If 2 people put in the same inputs, will it make the same machine?
So it depends upon the algorithm that they choose. Some of the algorithms that we had, like if you chose a linear regression, yeah, it would reproduce the same thing. If you chose a decision tree, it would be slightly different, just because every time you run a random forest, you get slightly different number of trees there. But it's largely going to be very consistent in overall performance, but maybe slightly different characteristics and stock picks over time, or some of the return over time. And the same thing with the boosted Royale. There is some randomness to it. So every time you run it, it's going to be slightly different. But in general, that's kind of a good test, is if you run it and change things drastically, then it's not really a stable model. Most of the times you just see minor changes, but overall it's within the same ballpark of performance, I would say. It doesn't change drastically, but it isn't the exact same portfolio every time you run it, if that's what the question's really getting to.
Thank you, Stuart. We'll take one more question. You mentioned that markets are dynamic and the relationships between a stock and inputs change. How do you identify the dynamics using historical data?
I mean, that's a good question. So our machine tries to do learning as it goes through time. So so really the question is it needs enough information about that change in the past history to be able to start saying that that's an important factor. So I guess there are different things that you can see from our website that say how good it's been. We posted one that talked about the pandemic, how it kind of responded to that. In general, there's probably like anywhere from a couple of weeks to a month before the machine starts to detect that there's something different, and then starts to adapt and learn from that. But the more history you have, the better it is, and the stronger that signal will be. So really, it's kind of like if something changes and you're only a week into it, the signal will start to show up, but it may be very weak, and then it'll start to grow as more and more of that information gets built into the history that it's learning from. So that's one of the challenges with using machine learning is it's going to take a little bit of time to adapt to what's going on in the market, and then start to make forward-looking predictions that kind of take that information into account.
Thank you, Stuart, for taking the time today and doing a great presentation. I would also like to thank everybody for joining us today. The presentation recording will be sent in an email within the next day. Have a great rest of the day, everybody. Thank you.
Thank you, everyone.